Title of my presentation is stochastic equation of a porous medium with fractional Laplacian and white noise. Of course, this is very wide direction and mathematics, and we deal with little bit with fractional calculus, with nonlinear groups, also with stochastic analysis. The stochastic porous medium equation is a filtration model, and encountering and the modeling of various phenomena such as fluid dynamics, stochastic, underground aerodynamics, astrophysics, and statistical physics. Too many sources we have in this science, in this direction. I would like to express about very solid contribution of Soviet mathematics in porous medium equation. I mean academician Zendovich, Kompanets, Barenblatt, Zheltov, and many others. It is about 20 centuries, mostly. But now, in our time, this kind of equation have a very good development and mathematical schools and Spain. In Spain, Professor Vasquez, Professor Arturo Di Pablo, many people work in this direction. I try a little bit to explain this kind of sources. In a number of works by Arturo Di Pablo et al. Developed the theory of existence and uniqueness for the equation of a porous medium with a fractional Laplacian of the form 1-1. It is not stochastic equation, it's deterministic case. You can see minus delta and alpha over 2. This is a fractional Laplacian, and also we have a nonlinear function modulo u on m-1 by u. We have a Cauchy problem here. We talk about this equation on whole place or n. Initial functions belong to integrable space of integrable function L1. Fractional order between 0 and 2, and porosity index m is a positive number. The existence of this uniqueness theorem for weak solution is proved for m less or equal to m star, like this. N is a dimension of our space. Our space is or n, like this. On the basis of L1 contracting semigroup theory, we have a theory of existency and uniqueness, also about continuous dependence of initial dates. We have a condition which enough for well-posed setting of this problem. Another cycle of works belong to Romanian mathematician Barbu, Euler Barbu, and his co-worker is devoted to stochastic equation of porous medium NRN of this kind of form. We have right size, we have a stochastic random perturbation. Here, Wt is a Wiener process, like 1,3. Here, beta k, that is a independent Brownian motions, that is a sequence of the probability space, like this. And Ek is orthonormal basis and fractional Sobolev dual space. The existence and uniqueness theorem proved and paper belong to Barbu and et al. Under the additional Lipschitz property with respect to function g. G is a coefficient under right part of our equation. It is noted that despite the limitations of generality, the Lipschitz property requirement, it is not in general case, but this case when nonlinearity have a Lipschitz property. There exist physical models describing such equations. For example, the two-phase transient Stefan problem perturbed by Gaussian white noise is such a model. And also, I want to express my. I want also to talk about other group of authors work. For example, paper Konas Khoshnavesyan, this mathematician from Illinois University. This group of scientists deal with Cauchy problem for nonlinear stochastic heat equation. Like 1.4. We also have here initial function u0. Here L, this is a generator, infinitesimal generator of Levy processes, stochastic process Levy, with the Levy exponent psi, normalized like this. Mathematical expectation presented through this identity. For h xi and t, positive, non-negative t, sigma is a Lipschitz, sigma in nonlinearity, Lipschitz continuous function. W point, it is white noise, and time and space. The initial function is a Borel measure. It is not integrable function, belong to L1. It is a more general, in this paper, more general function like Borel measure on R. It is well known that the fractional Laplacian in the one-dimensional case is the infinitesimal generator of the stable Levy processes. This is a well-known fact. The existence and uniqueness theorem for a weak solution of problem 1.4 was proved by this author, Konas Khoshnavesyan. More precisely, it was established that from the condition like this, delta from beta this integral is exists, then no. Follows that if U0 is Borel measure on R, it satisfies the integrability condition like 1.5, where P mu, PS mu, P beta mu belong to Banach space of predictable processes with norm like this, and X k, this is a norm like mathematical expectation from X k for all k from this half of interval. X belong to LK space. Then there is a unique element from this Banach space, such that xt almost certainly satisfies this relation. Here, star denotes the space-time type of stochastic convolution. Yeah, yes, okay. We have in this kind of papers, we have a new definition for stochastic convolution. It is a totally probability definition. It is and deterministic case we have a convolution for two functions. We have a stochastic convolution for two stochastic processes, and this kind of works. Okay. In our paper, in our presentation, we consider the generalized stochastic equation of porous medium with fractional Laplacian, and multiplicative, I'm sorry for this words, multiplicative white noise like 1.6 with initial condition like 1.7. The term of the right side of equation 1.6, G U W point T like this, describes random noise depending on the state of the system, and is L2 or N valued FT adapted Wiener process defined on the complete probability space with expectation Y and normal filtering like this. The operator minus delta alpha belong to 0, 2 denotes the fractional power of the Laplacian given on 6. This is a job of Deprade et al. The number M is indicator of the porosity of the medium. Okay, we talk about this Cauchy problem N or N. Okay. The main contribution of our work is the establishment of properties of existence, uniqueness, and regularity of soft or strong solutions of fractional stochastic equation of porous media. The obtained statements are generalization of the result of these works. I'm sorry, it is not only, we must talk not only about this group of authors. Many people work in this direction, but we deal with this only works. The presentation has the following structure, and the Section 2, we introduce Sobolev function spaces of integer and fractional orders needed below, and give a definition of soft solution to problem 1.6, 1.7. And section 3, fractional functional inequalities. We talk about the several fractional functional inequalities relevant to our work. And in section 4, our presentation is devoted to the main results of the existence, uniqueness, and regularity of solutions to problem 1.6, 1.7. Okay. Here, we collect information about functional spaces, functional spaces type of Sobolev, not only Sobolev space with integer degree, also we have here Sobolev space with fractional degree also. I think I not need talk about all of this, okay? This is more or less standard, from my point of view, standard information, okay? This is a phi, Gothic phi is a Fourier transform of function phi. We have a dual space, h minus 1. Also, we have h minus alpha. We have a lemma like this. If let n greater or equal to 3, then we have inclusion like 2.7. This h belongs to this space L. 2n divided by n minus 2. N is the dimension of our space. Also, we have an inequality like this. It is neat in our future construction. It should be noted that 2.7 does not hold for n less or equal to 2. However, due to the duality relation, we have inclusion like this, 2.8. Section 3, we talk about fractional equation of porous medium and deterministic case, okay? We talk about equation 3.1 and initial condition ux0 is equal to u0x, like this, where f belongs to Sobolev space, dual Sobolev space, U0 x from L1, this is integrable function, and the noun function u can be any side, any segment. We will assume that the fractional degree between 0 and 2, degree of porosity is m. In the limiting case, when alpha we give limit to 1, we obtain the standard standard equation of porous medium, like this. Standard equation of porous medium, which is the main model for nonlinear and degenerate diffusion. I talk a little bit, or I already talked about authors which deal with this kind of equation. It is very huge literature. We have, okay, our uh, our presentation devoted to fractional stochastic porous medium equation. A few words about this non-local operator, about minus delta alpha divided to 2, known as the Laplacian of order alpha, is defined for any function g from Schwarz class. Schwarz class is infinity time differentiated function function g belong to Schwarz class, and via Fourier transformation, we can write identity 3.2, because if we give minus delta alpha divided to 2g as h, then Fourier transformation for h, this is we can define like 3.2. This is a model of psi alpha and alpha degree by g Fourier transformation from function g. If we have alpha between 2 and 0, then we can also use the representation in the sense of the hypersingular kernel, like this. This is a principal value. And coefficient, this is a normalization coefficient, like this. The education of the form 3.1 can be considered as a fractional diffusion version of EPM. At the same time, equation of this kind can be considered as a nonlinear version of linear fractional diffusion equation obtained for m is equal to 1. If we take m equal to 1, we have a diffusion equation, which have the following solution representation. I mean, diffusion equation, where k alpha as the Fourier transform, like this. This means the kr kernel as the form, like this. For some profile positive and decreasing function f capital that behaves at infinity according to this rule. Okay. Yes, time, big problem. But I don't talk about inequalities and section 4. I move to section, in section 4, I move to section 5. This is some fractional inequalities. I don't talk about it. I go to main results. First of all, I want to explain this inequality 5.1. This is important need for us and our theorems. This inequality place for function from dual Schwarz space, the space of generalized function like S prime or N, and the Brown least, not Brown movement, but Brown least, because W depend on time and space jointly. And zero mean quadratical integrable Levy process on a suitably chosen Hilbert space, denote as covariance operator by K, by capital K, and we have for all W from this space, this inequality. Next statement, lemma 5.1, there are N and C such that we have this inequality, and next assertion established that W can be represented as a specially stationary random field on R and zero and infinity by T. This is a theorem about existence of our equation for solution for our equation. If the spectral measure mu of the process W is finite, then W can be identified as a random field as follows. Through this integral, let us now return to our equation. We multiply our equation by test function. We came to weak solution from this through this construction, and if we integrate by u by parts, and then we obtain 5.3. It is a presentation for u and weak sense. Okay, then we have a this is our main theorem. Suppose U0 from L1 and let U from this space, functional space, for all t greater than 0 is a weak solution of problem 1,1. Um, yes, in our case we take only non-negative solution. If we have this must belong to this space, and W satisfies inequality 5,1 and the condition of lemma 5,1, then this inclusion is true, and we have a for integral of our solution this kind of relation. Okay, I don't talk about proof, unfortunately. Not time for this. Yeah, okay. Also, we have one clarification for our equation, like this inequality, 5.4, and this is references. And thank you.
Thank you so much.